going into our second day of graphing rational functions, and these first two examples deal with rational functions with two vertical asymptotes. So the very first thing that you always want to do whenever you're graphing a rational function is to factor both your numerator and denominator. In this case, we'll need to factor the denominator. So our numerator is just x minus 2, can't be factored any further. And then x squared minus 5x plus 4, we've got a quadratic trinomial, so two numbers that multiply to 4 and add to -5 are -4 and -1. So this factors to x minus 4 times x minus 1. So we're going to use our acronym AIM to graph this rational function, and the A stands for the asymptotes. So first we're going to look for our vertical asymptote, then the horizontal asymptote. So the vertical asymptote, we're just going to set our denominator equal to 0. In this case, the x minus 4, we're going to set x minus 4 equal to 0. So we're going to set each of those factors equal to 0. So x minus 4 equals 0, add 4 to both sides, x equals 4. That's a vertical asymptote. Then we're going to set x minus 1 equal to 0. So x will equal +1. So these x values are the values. If we plug them in for x, they would create a 0 in the denominator. And obviously, since you've got two factors multiplied by each other, if either one of them were 0, then you would have 0 in your denominator. So let's graph those two vertical asymptotes. The first one is at 1. So there's where 1 is on my x-axis. So there's my first vertical asymptote. At x equals 1, it's a vertical line, so it's just x equals that number. Then I'm going to graph x equals 4. And there's my other vertical asymptote. So you can have many different vertical asymptotes. Now let's go for the horizontal asymptote. So we're looking at the highest exponent basically. And in our numerator, that's essentially x to the first power minus 2. And then in our denominator, we have a quadratic. So we have what I like to call more on the bottom, which means our horizontal asymptote is just y equals 0, which is just our x-axis. So y equals 0, that's an asymptote. So now we're going to find what is designated by the I in AIM, the intercepts. So we're going to look for our x-intercept, and then we're going to look for our y-intercept. So the x-intercept, remember, that's the solution to the top. The x-intercept is when y is 0. So if I set my numerator, which is x minus 2, equal to 0, then x would equal 2. And we're going to write this intercept as an ordered pair. And the x-intercept is when y is 0, so I'm going to write it just like this, and I can graph it just like that. The y-intercept is when x is 0, so I'm just going to plug in 0 for x, and I can plug it in my factored form, or I can plug it into the x squared minus 5x plus 4. In this case, I'll just plug it into the factored form. 0 minus 4 times 0 minus 1, so I get -2 over -4 times -1, which is +4. -2 divided by 4 just simplifies to -1/2. So I'm going to write that as an ordered pair, -1/2. So 0, -1/2. If there's -1, -1/2 is like right there. So now the M, I'll write that over here, and AIM stands for multiplicity. Do we have any of those special squared terms where the entire factor is raised to a multiple of 2, like 2 or 4 or 6? We do not, so it's not applicable. So now we've got these multiple vertical asymptotes. We have an x-intercept, so this is really the first time you're going to see an x-intercept on that horizontal asymptote, and that is absolutely okay. So a lot of students really they get confused. I thought an asymptote was something, a function just continuously approached and never crossed. Well, that's on the ends of my function. So one end being that way and the other end being this way. So like essentially outside of those two vertical asymptotes. If it's inside those two vertical asymptotes, your function can cross it. And you might see it do that in other special scenarios as well if you continue into pre-cal calculus. You'll see some special examples where it'll like cross your horizontal asymptote and then it'll like go back down, you know, and it'll continuously approach that asymptote. And those are, you'll just see some funky stuff like that. But generally that's kind of a good rule for Algebra 2. So the question is, what does the rest of this function look like? Well, I know that because I have, let's call this like this lower left quadrant, my y-intercept, I know it's going to approach that asymptote there and that asymptote there, and I know it's going to look like that. So now what is the middle part of this function going to look like in between those two vertical asymptotes? Well, because there is no multiplicity, I know my function isn't going to meet or come together at any of these vertical asymptotes. So it's really going to go, this function is going to go up to this way on this asymptote, and then it's going to come down and look like that at that asymptote. So it's not going to meet, which means if I'm looking at like maybe the right side of the vertical asymptote x equals 4, what's the function going to look like? It's going to be in like this upper right quadrant, if you will. It's going to look just like that. And then you can graph it on your graphing calculator and make sure you graphed it correctly. You can always plug in points, like where is it at if I were to plug in a 3? You know, if I plug in 3 for x, well, I'm going to get a negative value for y. So I know it's going to be, you know, down here. So let's move on to problem number 2. In problem number 2, what do I need to do first? I need to factor that denominator. So if we factor that denominator, x minus 1 is factored. And then this is a quadratic trinomial. Two numbers that multiply to negative 12 and add to negative 4 are negative 6 and positive 2. So x minus 6 times x plus 2, factoring is obviously a key component when graphing rational functions. So if you need to go back and review factoring, I would highly suggest doing that. So we factored this rational function, and now let's look for the asymptotes. Let's first look for the vertical asymptotes. So what do I do to find the vertical asymptote? I plug in each of those factors. So I'm actually going to have two vertical asymptotes because I've got one factor, and if I solve for x, I get x equals 6. And I have this other factor here, x plus 2. And if I solve for x, I get x equals negative 2. And now let's find our horizontal asymptote. So the horizontal asymptote. So as you can see, if we go back to the original one, I have the basically highest exponent, right, is a 2. So if I actually multiplied x minus 1 times x minus 1, I would have that you could see that x squared, and then I have x squared right here in my denominator. So it's actually the same. And when it's the same, then it's y equals the ratio of the coefficients, which is just going to be 1 and 1. So y equals 1. Remember, it's the ratio, so y equals 1 over 1. If you want to write it out like that, you absolutely can, but y equals 1. So now let's graph these asymptotes. So the first one I'm going to graph is x equals negative 2. And then the next one is x equals 6. And then let's graph our horizontal asymptote at y equals 1. And now we can look for the intercepts. So the intercepts are the solution to the top. So I'm going to set my numerator equal to 0, and I have x minus 1 squared. So I'm just going to set x minus 1 equal to 0. And when I solve for x, I get x equals 1. And if I write that as an ordered pair, I get 1, 0, right? The x-intercept is when y is 0. So I know my x-intercept is at 1, 0. So now let's look for the y-intercept. The y-intercept is when x is 0. So I'm just going to plug in 0 for x. And I'm going to plug it in for x in this factored form, right? So I'm going to plug it in right there. I'm going to plug it in right there. And I'm going to plug it in right there. So I get 0 minus 1 squared over 0 minus 6 times 0 plus 2. which is 0 minus 1 is -1. -1 squared is +1 over -6 times +2 is -12. So this is 0, -1/12. So what does that tell me? That tells me that it's negative, right? I know my function is going down just like that. So now I'm looking for the m. What does the m stand for? Multiplicity. Do we see any of those special squared terms where the entire factor is squared? We do. We see it right up here in our numerator, x minus 1 squared. So yes, we do have multiplicity. Where is it? It's in the numerator. So in the numerator, well, what does that do? You know, if it's in the denominator, that's when your function meets at that asymptote. If it's in your numerator, that means it's going to have a double root bounce at that root, right? Because the numerator, the solution to the top gives us our x-intercept, right? The solution to the bottom gives us our vertical asymptote. So where those special squared terms are, determine, is it a double root bounce or is it going to meet at that asymptote? It's in the numerator, so it's going to occur at that x-intercept, so at the point 1, 0, and it's going to be a double root bounce. So what does that look like? Well, that means at this point 1, 0, obviously my function's going to go like this. And when you have a double root bounce, it just bounces off and it comes back like the same direction. So it's not going to go above y equals 0. So it's going to come back down. It's not going to cross it, and it's going to go down to at the asymptote x equals 6. So then where is the rest of the function? Where there's no multiplicity in the numerator, so it's not going to meet at any of these asymptotes, which means the rest of the function is just up here, right? And then over here. And that's what your function looks like. And you can obviously grab your calculator or graph it in Desmos, something like that, and make sure that you have graphed it correctly. Moving on to number 3. Number 3 is an example of a rational function with holes. Again, so this one will have a hole. So on number 3, what's the first thing that we want to do when we're graphing rational functions? We want to factor. So in this case, we actually need to factor our numerator and our denominator. So when I factor the numerator, I can factor out a GCF of x, and I'm left with x plus 2. When I factor that denominator, it's just a basic trinomial, and it's going to factor x plus 2 times x minus 1. So in this case, I have the same factor on top as I do on bottom, x plus 2 over x plus 2, which means my new function after crossing those out is x over x minus 1. So where is the hole at in this function? Well, I set that factor, which is x plus 2, equal to 0, and I find that that x value of that hole is at -2. Well, what would be the y value? If I take that that -2, and I plug it in to x over x minus 1, I'll get the y value, which would be -2 over -2 minus 1, which is -2 over -3, which is just 2 over 3. So I can say this function will have a hole, so with a hole at the point -2, 2/3. So I need to just kind of signify that on my graph with just an open dot. And now we're going to use the x over x minus 1 to find the vertical asymptote and the horizontal asymptote. So the vertical asymptote is just the solution to the bottom. So I'm going to set x minus 1 equal to 0, and I solve for that vertical asymptote, which is at x equals 1. The horizontal asymptote, I'm looking at the degree of the numerator and the denominator, and I can see that I have an x, which is just x to the power of 1, and then the degree of the denominator is just x to the power of 1, so they are the same, which means the horizontal asymptote is the ratio of the leading coefficients of each of those the numerator and denominator, which is y equals 1. So now let's graph those asymptotes. So x equals 1 is going to be right here. That's the vertical asymptote. X equals 1, and then y equals 1 is the horizontal asymptote. So now let's look for the x-intercept. What do I do to find the x-intercept? The x-intercept is when y is 0. If I plug in 0 for y, then what I'm finding is the solution to the numerator. So x equals 0, which is just 0, 0. So that x-intercept is the solution to the top. The y-intercept is when x is 0. So if I plug in 0 for x, well, that's just 0 divided by -1, which is just 0. So my x-intercept and my y-intercept are the same right here. And now we're looking for any multiplicity. Do we have any of those special squared terms where the entire factor is squared? We do not. So this is not applicable. So what does this function look like? Here's the rest of the function. So the function in this lower left quadrant is going to approach this asymptote down here. Don't forget we have a point, or we have a hole about right there, and that's how we signify that hole in the function. So that's what it's going to look like on the left side of that vertical asymptote. On the right side of that vertical asymptote, because it doesn't meet at that asymptote, I know the rest of the function is going to be above that horizontal asymptote, just like that. So rational functions that are actually linear. So again, the first thing you want to do is factor your numerator and denominator. And in this case, we only need to factor our numerator. So how is it going to factor? X plus 6 times x minus 1 over x plus 6. And as you can see, we obviously have a hole in this function. Where is that hole? Let's see, I'm going to go ahead and rewrite this x minus 1, put a little box around it. And where is that hole? I'm going to set that x plus 6, that factor that I have that's the same on top and on bottom, equal to 0. And I get x equals -6. That's the x value of the whole of this function. So what's the y value? Well, I'm going to take -6 and I'm going to plug it into this function right here. So -6 minus 1 equals -7. So this is actually linear and with a hole at -6, -7. So if I were to graph x minus 1, or y equals x minus 1, f of x equals x minus 1, my y-intercept is at -1. My slope is rise 1, run 1, right? So I'm just rising 1 and running 1, just like this, right? And I know I'm going to have a hole at -6, -7, right? So -6, -7, it's like down here. There's the hole. And this is what your function looks like. So this is an example of a rational function that is actually linear because there's a hole in the rational function. So it's actually linear. So let's move on to our last and final example. So the first thing that I want to do in this example is I'm going to factor this. And I have a difference of squares. It kind of looks like it's already factored, but we're going to rewrite it. X squared minus 16 is a difference of squares. And that's x plus 4 times x minus 4. So actually, if I were to rewrite this, -6x over, what would you do? I would combine x minus 4 and this x minus 4 squared times x plus 4. So now I've rewritten it and I can see that I have multiplicity in the denominator. I have that special squared term, or the entire factor is raised to a multiple of 2. So now we're going to use this and we're going to find the vertical and the horizontal asymptotes of this function. The vertical and the horizontal asymptotes. So the first thing we're going to do is find where those asymptotes are. So I'm going to set each of those factors equal to 0. X minus 4 equals 0, and I get x equals positive 4. There's one of the vertical asymptotes. Then x plus 4 equals 0, so x equals negative 4. And the horizontal asymptotes, again, you're looking at the highest exponent in your numerator and denominator. Where do you have more x's, if you will? We have more on the bottom. And because of that, it's just y equals 0, which is just our x-axis. So let's graph those vertical asymptotes. X equals negative 4 is right here. Whoa, could have graphed it better, but oh well. And then x equals positive 4 is over here. And then y equals 0 is just that x-axis, right? So now, next step, we're looking for I, which stands for intercepts. So we're going to look for our x-intercept. Then we're going to look for our y-intercept. And the x-intercept is the solution to the top, right? Because we're plugging in 0 for y, and that's what we end up having to do. So negative 6x equals 0, which is x equals 0. So our x-intercept, if I were to write it as an ordered pair, is 0, 0. So it's at the origin, right there. What about the y-intercept? The y-intercept is when x is 0. So if I plug in 0 for x, I get negative 6 times 0 over 0 minus 4 squared times 0 plus 4, which 0 divided by anything is just 0, which means my y-intercept is at 0, 0 as well. So now, my last thing with the aim is multiplicity. Do I have any multiplicity in this function? Any of those special squared terms? Yes, we do. We do have multiplicity. It's in the denominator, which means this function will meet at x equals positive 4. That's that asymptote. The asymptote for x minus 4 squared is at positive 4. So it's going to meet at this asymptote over here, x equals 4. You can just kind of write that right there. It's going to meet at that asymptote. So the question now becomes, well, I really don't have enough information to finish this graph. Remember, but where does it meet? You can always, always, always plug in a point. Plug in a point. So what point do we want to find in this function? We could find when x is 1, when x is 2. Let's find f of 1. So if I were to plug in 1 in this function, that would be negative 6 times 1 over 1 minus 4 squared times 1 plus 4, which becomes negative 6 over, let's see, that's negative 3 squared, that's 9 times 1 plus 4 is 5, which is, if I were to rewrite it again, negative 6 over positive 45, which I could divide by 3 and simplify to negative 2 divided by 15. So what does that tell me? That tells me that 1 negative 2/15 is a point on this graph, which if I'm just kind of just generally sketching this graph, I know that positive 1, it's actually negative down here, right? So that tells me that this function is going to have this general shape. In the middle of these two asymptotes, it's going to look just like this. Because there's not a double root bounce or anything like that at that x-intercept, it's going to take that general shape where it kind of looks cubic in the middle of those two asymptotes. Well, then what does the rest of the function look like? On the left side of x equals negative 4, I know the function is going to be down here below that horizontal asymptote because it doesn't meet at that vertical asymptote. Now let's look to the right side of this x equals 4. To the right side, we have multiplicity at this asymptote, which means it's going to meet at this asymptote. It's going to come together right there. So this is one of your more challenging problems right now. You can always plug in a point just to kind of see, well, where is it really at? Right here. What about this point? What about when x is -3? You could have plugged in -3 and you would have gotten a positive y value. So that concludes your notes over graphing rational functions. Day 2, it was a little more challenging than day 1. If you're still confused, you can always go back to that first video and see if you can maybe grasp some of those concepts a little bit better, but I hope it was helpful.